Hello everyone, I'm Alba. Welcome to Lecture 3 of Machine Intelligence I. Today we'll explore how calculus helps machines learn through the example of linear regression. We'll start with a short calculus review, learn how gradient descent finds the best model parameters, see how the ordinary least squares method gives an exact solution, and finally, we'll extend linear regression into polynomial or nonlinear regression. Let's get started.
Why calculus matters? Machine learning models learn by minimizing error, where we adjust parameters called theta until the cost function j becomes as small as possible. This process is called optimization. It's how learning happens. To understand the meaning of learning, imagine j as a landscape. Each theta is a location, and the height is the error. Learning means moving downhill, searching for the lowest valley, where the model performs best. Now the derivative tells how fast j changes when we move theta. Positive slope means the error increases. Negative slope means it decreases. Zero slope means we're on a flat region, maybe a minimum. To understand the slope concept, please think of j as a hill. If the slope is positive, we climb uphill. If it's negative, we roll downhill. At slope 0, we've reached a flat spot, the top or the bottom. Now, when j depends on several thetas, we take a separate derivative for each one that is called partial derivative. Each shows how sensitive the error is to changes in that specific parameter. With two parameters in our example, j becomes a surface. Each point has a height showing the error. The gradient is the steepest uphill direction on that surface. So the gradient will collect all these partial derivatives. It will then point toward where the error increases fastest. To minimize j, we go the opposite way, downhill along minus the gradient. Now we can control learning. Each update subtracts a small step of the gradient, scaled by alpha, the learning rate. This simple rule is called gradient descent. Applying this idea to a real model, we predict y from x using y equals theta naught plus theta 1 times x. We'll find theta values that minimize the mean squared error. If we try many slopes, we get a U-shaped curve. Wrong slopes make big errors. The best slope gives the lowest j. That's where the model fits perfectly. So gradient descent repeats 3 steps. Calculate the gradient, move a bit downhill, and repeat until changes become tiny. At the start, the slope is steep, so steps are big. Closer to the minimum, the slope flattens, and steps become smaller until we stop at the valley floor. Let's code one step of the update for gradient descent in Python. We compute predictions, measure the gradient, and update theta. Please now try changing alpha. A small value moves slowly, a large one may overshoot. Moving to the next slide, an important question is raised. What do the learning rate do? Basically, the value of alpha controls how fast learning moves. Too small, slow progress. Too large, unstable jumps over the minimum. Now we'll apply gradient descent to real data. We'll predict diabetes risk from BMI, load the dataset, normalize values, and run a few iterations. You'll see theta converge. Please try it yourself. Here's the learned line. The black dots are real data, and the red line is our prediction. You can see it captures the general upward trend. In linear regression, we can find the best theta directly without iteration, so let's discover how we can do that. Setting the derivative of the cost to 0 gives a closed-form solution, the OLS formula. We expand the cost equation, take the derivative, set it equal to 0, and solve for theta. This leads to theta equals inverse of x transpose x times x transpose y. What we can see now is that the OLS solution jumps straight to the valley bottom. Gradient descent walks there step by step. Both reach the same point, one by math, one by movement. In matrix form, x holds all inputs, y is the outputs, and theta is our parameter vector. Multiplying and inverting x summarizes all data into a compact equation. Geometrically, OLS projects onto the space formed by the columns of x. The blue arrow is the prediction y, lying in that plane. The red arrow is the residual, perpendicular, meaning no further improvement. In Python, we can compute theta directly with one line, inverse of xt.x times xt.y. It gives the same slope and intercept as gradient descent. When we print both results, they match almost perfectly, confirming that both methods reach the same minimum. Straight lines can't model curves. Polynomial regression adds x squared, x cubed, and more to capture curved patterns, still linear in parameters but non-linear in shape. Adding x squared lets the model bend smoothly through the points, fitting data better than a straight line. With scikit-learn, we can build a full pipeline, polynomial features to expand x, then linear regression to fit using OLS. It trains a curved model automatically. The pipeline connects each step. Input x goes through polynomial expansion, then linear regression, and finally gives predicted y. It's a clear flow from raw data to model output. Now please experiment that. Change the polynomial degree. Low degree underfit, too rigid. High degree overfit, too wiggly. The goal is balance.
So, by the end of this session, we saw how calculus shapes learning, how gradient descent finds minima, how OLS solves them directly, and how polynomial regression captures curves. Next time, we'll learn how to prevent overfitting with regularization.